Dark matter. It sounds like something out of a science fiction movie, right? But scientists say it's very real and it's one of the biggest mysteries in our universe. Everything you see around you, planets, stars, galaxies, only makes up about 5% of the universe. The rest? It's mostly dark matter and dark energy, but wait a second, is dark matter actually real? We can't see it, touch it, or even detect it with traditional instruments. Scientists have been trying to crack the dark matter code for decades. Some think it could be made up of exotic particles that we haven't discovered yet. Others speculate it might be a different kind of matter that interacts with our universe in ways we can't yet comprehend. But why should you care about something you can't see? To understand this, it's useful to differentiate dark matter into hot and cold types, with some even suggesting a middle ground of warm dark matter. The terminology refers to the mass of dark matter particles, which dictates their speed. Hot dark matter particles, being of lower mass, travel faster than CDM particles. The distribution of hot dark matter could help explain how clusters and superclusters of galaxies form post-Big Bang. Theorists claim there are two classes of dark matter. One, those that congregate around individual galaxy members within a cluster, and two, those that encompass the clusters as a whole. Hot dark matter, on the other hand, should correspond to the formation of larger mass aggregates that surround whole galaxy clusters. However, data from the cosmic microwave background radiation, as measured by the COBE satellite, is highly uniform. This uniformity implies that high-velocity hot dark matter particles cannot form clumps as small as galaxies, highlighting a discrepancy between dark matter theory and actual data. Thus, hot dark matter alone cannot account for cosmic galaxy formation, placing it under the larger umbrella of mixed dark matter theory. An example of a hot dark matter particle is the neutrino. Neutrinos have very small masses and do not partake in two of the four fundamental forces, specifically the electromagnetic and strong interactions. They interact via the weak interaction and most likely gravity, but due to the feeble strength of these forces, they are difficult to detect. Currently, projects like the Super-Kamiokande Neutrino Observatory in Gifu, Japan, are studying these elusive particles. In cosmology and physics, cold dark matter is a hypothetical type of dark matter. Cold refers to the fact that the dark matter moves slowly compared to the speed of light, giving it a vanishing equation of state. Dark indicates that it interacts very weakly with ordinary matter and electromagnetic radiation. Proposed candidates for CDM include weakly interacting massive particles, primordial black holes, and axions. As such, it is very difficult to determine what the constituents of cold dark matter are. The candidates fall roughly into three categories: axions, very light particles with a specific type of self-interaction that makes them a suitable cold dark matter candidate. Since the late 2010s, axions have become one of the most promising candidates for dark matter. Axions have the theoretical advantage that their existence solves the strong CP problem in quantum chromodynamics, but axion particles have only been theorized and never detected. Axions are an example of a more general category of particle called weakly interacting slender or slim particle, which are the low-mass counterparts. Massive compact halo objects are large condensed objects such as black holes, neutron stars, white dwarfs, very faint stars, or non-luminous objects like planets. The search for these objects consists of using gravitational lensing to detect the effects of these objects on background galaxies. There is no currently known particle with the required properties, but many extensions of the standard model of particle physics predict such particles. In the cold dark matter theory, structure grows hierarchically, with small objects collapsing under their self-gravity first and merging in a continuous hierarchy to form larger and more massive objects. Since the late 1980s or 1990s, most cosmologists favor the cold dark matter theory, specifically the modern lambda CDM model, as a description of how the universe went from a smooth initial state at early times, as shown by the cosmic microwave background radiation, to the lumpy distribution of galaxies and their clusters we see today. The large-scale structure of the universe. Dwarf galaxies are crucial to this theory. Having been created by small-scale density fluctuations in the early universe, they have now become natural building blocks that form larger structures. Several discrepancies between the predictions of cold dark matter in the lambda CDM model and observations of galaxies and their clustering have arisen. Some of these problems have proposed solutions, but it remains unclear whether they can be solved without abandoning the lambda CDM model. Cuspy halo problem states that the density distributions of dark matter halos in cold dark matter simulations, at least those that do not include the impact of baryonic feedback, are much more peaked than what is observed in galaxies by investigating their rotation curves. Dwarf galaxy problem states that cold dark matter simulations predict large numbers of small dark matter halos, more numerous than the number of small dwarf galaxies that are observed around galaxies like the Milky Way. Satellite disk problem states that dwarf galaxies around the Milky Way and Andromeda galaxies are observed to be orbiting in thin, planar structures, whereas the simulations predict that they should be distributed randomly about their parent galaxies. High-velocity galaxy problem states that galaxies in the NGC 3109 association are moving away too rapidly to be consistent with expectations in the lambda CDM model. In this framework, NGC 3109 is too massive and distant from the local group for it to have been flung out in a three-body interaction involving the Milky Way or Andromeda galaxy. Galaxy morphology problem says if galaxies grew hierarchically, then massive galaxies required many mergers. Major mergers inevitably create a classical bulge. On the contrary, about 80% of observed galaxies give evidence of no such bulges, and giant pure disk galaxies are commonplace. The tension can be quantified by comparing the observed distribution of galaxy shapes today with predictions from high-resolution hydrodynamical cosmological simulations in the lambda CDM framework, revealing a highly significant problem that is unlikely to be solved by improving the resolution of the simulations. The high bulgeless fraction was nearly constant for 8 billion years. Fast galaxy bar problem says if galaxies were embedded within massive halos of cold dark matter, then the bars that often develop in their central regions would be slowed down by dynamical friction with the halo. This is in serious tension with the fact that observed galaxy bars are typically fast. Small-scale crisis are the comparison of the model with observations may have some problems on sub-galaxy scales, possibly predicting too many dwarf galaxies and too much dark matter in the innermost regions of galaxies. This problem is called the small-scale crisis. These small scales are harder to resolve in computer simulations, so it is not yet clear whether the problem is the simulation's non-standard properties of dark matter or a more radical error in the model. Warm dark matter is another hypothesized form of dark matter that has properties intermediate between those of hot dark matter and cold dark matter. Interestingly, weakly interacting massive particles, when produced non-thermally, could also be candidates for warm dark matter. However, thermally produced WIMPs are generally considered cold dark matter candidates. One possible warm dark matter candidate particle with a mass of a few kilo-electron-volt comes from introducing two new zero-charge, zero-lepton number fermions to the standard model of particle physics. But in some scenarios, the entropy production from the decays of unstable heavier particles may suppress their abundance to the correct value. These particles are considered inert because they only have suppressed interactions with the Z boson. Sterile neutrinos with masses of a few kilo-electron-volt are possible candidates for Kevins. At temperatures below the electroweak scale, their only interactions with standard model particles are weak interactions due to their mixing with ordinary neutrinos. Due to the smallness of the mixing angle, they're not overproduced because they freeze out before reaching thermal equilibrium. Their properties are consistent with astrophysical bounds coming from structure formation and the Pauli principle if their mass is larger than 1 to 8 kilo-electron-volt. In February 2014, different analyses extracted from the spectrum of X-ray emissions observed by XMM Newton, a monochromatic signal around 3.5 kilo-electron-volt. This signal is coming from different galaxy clusters like Perseus and Centaurus, and several scenarios of warm dark matter can justify such a line. For example, a 3.5 kilo-electron-volt candidate annihilating into 2 photons, or a 7 kilo-electron dark matter particle decaying into a photon and a neutrino. As we delve deeper into the cosmos, we uncover more questions than answers. but each discovery brings us one step closer to understanding the universe. From the hot dark matter to the warm dark matter candidates and the cold dark matter, this ongoing scientific journey with each astronomical observation contributes to a larger picture known as universe.